Hi everybody. The next section that we're going to look at for aromatic substitution reactions covers activators and deactivators. But before we go further, I just wanted to review a little bit about the electrophilic aromatic substitution reaction. And let's just keep this super generic. So I'm going to start out with benzene. And what I'm going to do is show this reacting with a generic electrophile. And like we've seen before, if the electrophile is strong enough, then benzene, or some sort of substituted aromatic ring, can act as a nucleophile, and we can break aromaticity. And if you remember, when we break aromaticity, this is called a sigma complex. And one thing we haven't really emphasized before, but is also important to remember, is that this sigma complex has resonance, right? So we can move this pi bond around so that it has a positive charge that delocalizes. And I can move this pi bond down here to try to spread that positive charge around this entire ring system. So even though we're breaking aromaticity, which is energetically very unstable, at least we're getting some sort of benefit by having resonance to delocalize the positive charge. And then last but not least, we can do that final deprotonation, which I'll just call minus H+, using some sort of incredibly weak base to restore aromaticity, and we can get to our final product where our electrophile is just installed correctly and aromaticity is restored. All right, so let's break this down and then ask ourselves, all right, which of these reactions is going to be the slower reaction? Well, we know that breaking aromaticity going from here to here is energetically unfavorable, which means that this must be our rate limiting step. If we think about the other step, the second one over here, this is going to be really, really fast because we're restoring aromaticity. It very much wants to happen at that point because this intermediate in the middle is so unstable, it very much wants to go back to that aromatic product. All right, so when we're looking at these reactions, we can start studying the rates of these reactions. We can ask ourselves, all right, how quickly is this occurring? And beyond that, how can we make this reaction go faster? Meaning, how can we increase the rate of the reaction? And so that's where activators and deactivators come in. An activator is a substituent that increases the rate of the reaction. And I'm just going to call this our EAS, or electrophilic aromatic substitution reaction, just to save us a little bit of space right here. So it's supposed to make that rate limiting step occur faster, and there's two different ways that it can help this reaction to occur faster. One is by stabilizing the transition state through resonance or induction. So let me write stabilizes, and then I'll say transition state double dagger. Or induction. All right, so let's take a look at a handful of these activators, and we'll start analyzing them in more detail. So let's start out with the strong ones. We know that strong activators are going to be substituents that really increase the rate of the reaction, and we know that it must stabilize the transition state either through resonance or induction. So let's figure out what's going on here. And experimentally, we know that things like phenols are strong activators. So what I mean by a substituent here is this alcohol group is acting as a strong activator. Or we could say that aniline is a strong activator. All right, so let's take a look as to why. All right, so in this reaction, we're going to have our electrophile, positive charge, and we know that this electrophile in this case must be very strong in order to react with our weak nucleophile benzene. All right, so our aromatic ring is attacking in, and when we do this, we again are going to break aromaticity and give us this sigma complex right here. But that's okay because we know that with these sigma complexes, we have a lot of resonance that can occur. So let's go ahead and draw the resonance structures for this sigma complex. So I'll go ahead and draw this ring where we move the pi bonds around. And if we do that, let me just keep it consistent here. We would have a positive charge right here, and we can delocalize it even further by moving that pi bond over. Which would put the positive charge on the other side of the ring. However, there's actually one more resonance structure, and that resonance structure is due to the oxygen lone pair. So if we think about this, right, this oxygen lone pair can actually push down and delocalize all the way down into the ring system. Which gives the oxygen the positive charge. All right, so it kind of makes sense that this is going to be a more stable intermediate because it has more resonance structures, and it has more resonance structures due to this OH group donating its electron density in. So this is a really excellent example of a strong activator. All right, the other question I could ask is, which of these resonance structures is the major contributor? And if you remember way back to first term, the major contributor is going to be the one where all of the octets are full. So this would be our major contributor because over here we've got an octet rule violation, and octet rule violation. We know that when we're assigning major, minor resonance contributors that full octets take priority. So strong activators have these transition states, or intermediates for that matter, that are really resonance stabilized. So we could go ahead and we could do the exact same thing down here, but you get the idea. The idea with these is that they have electrons that can be donated into the ring, thereby stabilizing the transition state. And intermediate. All right, so that's kind of a cool example of strong activators, is either having an alcohol or an amine coming off of an aromatic ring. Very stabilizing. All right, now let's take a look at the moderate activators. And as you can imagine, moderate activators are still fast, but not as fast as the strong activators. So they're kind of in the middle here. So let's take a look at what's going on with moderate activators. All right, with moderate activators, we've got a situation like this, where you'd look at this and you'd say, well, I've got a lone pair here that can donate electron density into the ring. So wouldn't this be the same example as above, where it could stabilize the transition state and intermediate? Yes, absolutely. However, it does have resonance where it's pulling in the other direction. So the main feature with these is that they have competing resonance. So it has competing resonance pathways. And because of this, it's not as powerful as resonance that exclusively goes into the ring. All right, let's take a look at another one. All right, the other one I wanted to look at is pretty similar, where same idea. We could take this nitrogen lone pair and we could say, hey, we can dump this into the ring, or we can pull this over to the oxygen. Same idea. Both of these have competing resonance, therefore they're considered moderate activators. All right, I'll show you the weird exception. And unfortunately in chemistry, there's a lot of these weird exceptions. However, we just have to live with them. And this exception involves something like this, where you have an alkoxy group. So anytime you see an R group like this is going to be an alkyl group. So that could be a methyl, ethyl, tert, butyl. It doesn't matter, some sort of sp3 hybridized carbon. And when you look at this, a lot of times students will say, well, this one can only do resonance into the ring, right? So the only resonance pathway I see is one in which it can push electron density into the ring. Shouldn't this be a strong activator? It doesn't have competing resonance. Not so much. We know experimentally that this behaves much more like the example shown right above it. So this one is also a moderate activator. We're really not going to get into the why behind that. The main reason we know that it's a moderate activator is simply from kinetics studies. So when we experimentally do this, we see that this one down here behaves a heck of a lot more like both of the two examples above it rather than the examples up here. So it just falls in this category much more nicely. All right, let's look at weak activators. All right, so let's take a look at weak activators really quick. And weak activators are going to be things that are alkyl groups typically. So we've got some sort of alkyl group. And like I said, an alkyl group could be a methyl, ethyl, tert, butyl. Anything with an sp3 hybridized carbon counts as an alkyl group here. So then the question is, well, why are these activators? There's no resonance occurring here. All right, well, let's take a look at this more closely. So let's imagine that our alkyl group is a methyl group. So it's got a CH3 coming off of it, and I'm going to show all of those hydrogens. If you look at an electronegativity table, hydrogen's actually slightly more electronegative than carbon. Oops, sorry, I've got those going backwards. Carbon's slightly more electronegative than hydrogen, so my arrow should be going this way. There we go. So if you look at the electronegativity table, hydrogen's, I think, about 2.1 and carbon's 2.5. So carbon's slightly more electronegative, which means that this carbon is electron rich, at least somewhat. All right, so if we think about it being electron rich, that means that it can donate some of its excess electron density into the aromatic ring through induction. So let's make a note here. So it donates small amount of electron density via induction. All right, so that's kind of the weird example, not nearly as strong as resonance where you're pushing lone pairs of electrons into the ring. This is just a weak inductive force where the carbon being so electron rich can actually share a little bit of that excess electron density into the aromatic ring. All right, last but not least, I wanted to talk about regiochemistry. All right, so we already talked about all of these where they stabilize the transition state where we're breaking the aromatic ring, and they stabilize the intermediate that results, but we haven't talked about regiochemistry. So let's briefly take a look at this. So I'm just going to use one of our strong activators, phenol. And my question is, will the electrophile attack here? Will it attack here? Or will it attack here? Well, let's try to predict, right? So in this case, it makes sense if we think about this using resonance, right? So I'm going to erase these arrows, and I'm going to say, all right, let's draw all the resonance structures we can. So if I do this, I can show resonance where I delocalize a lone pair over to that carbon, resulting in a positive charge on the oxygen above. And then I can keep on pushing this lone pair all the way to the bottom carbon. That gives me a negative charge right here. And then I can keep on pushing this all the way over here. Where I've got a negative charge over on this side of the ring now. And then last but not least, I can push this all the way back and get my last resonance structure. Oops, this should be a single bond up here. Almost had a Texas oxygen, or sorry, Texas carbon, even worse. All right, so we've got all of these resonance structures for my aromatic molecule, in this case, phenol. All right, now let's think about the hybrid. All right, the hybrid view, if you think way back to the first term, was where we showed kind of the average picture of what's occurring here. So we know in this average picture that the aromatic ring doesn't really contain any true alkenes. It's more in between single and double bonds. So I'll show that using a dashed circle on the inside. And we know that the bond between carbon and oxygen isn't a true single bond and it's not a true double bond. It's kind of in between. So I'll do that. And then we know the bond to hydrogen is always going to be a single bond. All right. So let's take a look. We know that the oxygen in some of these structures carries a positive charge. Whoops, this should be positive right there. So when we go to our hybrid structure, we could say, well, that oxygen must be partial positive, right? Because at least in some of the structures, it carries a positive charge. All right, if we think about where the negative charges are, we could say, well, there's a negative charge right here, and right here. So there must be partial negative charges in those positions. All right, so we've got this hybrid view that we can look at, and we can ask ourselves, all right, if you're thinking about this reaction where this is going to react with an electrophile, which carbons do you think are more likely to react with the electrophile? Well, in this case, it seems quite clear that these partial negatives are going to be really attracted to the positive charge on the electrophile. So in this case, you could show either one of these acting as your electrophilic source. In this case, the one over on the left-hand side is symmetrically the same. So what you might expect in the end is to get an electrophile down here installed and an electrophile over here. Both of these seem like reasonable pathways or reasonable products based on the resonance structure for our starting material, right? So my take-home message for this is that activators are typically what we call ortho-para-director. And what that means is the electrophile that gets installed is either going to be para, like this example, or ortho, like this example. So we can predict the regiochemistry of our final product. And this is really important, especially as we start planning out synthesis problems. All right, so that's where I'm going to stop right now. is talking about that regiochemistry. What we'll do next is we'll take a look at deactivators and come up with a solution for figuring out how they work.